Okay, thanks a lot. Okay, so let me first write the title of my talk. I will talk about selector form of Weaver's ASR, well, conjecture, now it's a theorem, and I'll talk about frame sparsification or maybe discretization. Okay, so let me start by explaining to you what is a Weaver's from the Weaver's ASR, well, still a conjecture, even though now we know it's a theorem. So it's very easy to, it's very simple formulation, but I wish, well, I knew about this before, but okay, well, now it's, okay, so you start from a finite collection of vectors, right, in d-dimensional space, and you assume, well, maybe you have also some kind of parameter delta positive. So, so you assume that this collection of vectors forms something which is called Parseval frame. So what happens is the following. So I'll just write. So when you take inner products against UI, you get, let's say, equal to 1, or maybe the norm of U for or U in, right? But you also assume that, in addition to this, you assume that the norms of your vectors are small. Let's say there's less than delta. So now what you would like to do with those vectors, maybe let me just say the following in terms of conjecture. We claim that there exists delta and there exists, let's say, epsilon positive. So what we'd like to do, and maybe let's say there exists also an R, right? I mean, so that once you take those vectors, you can decompose them into Bessel sequences which we have smaller norm. So what is the conclusion? Then there exists, let's say, partition I1, IR of our index set. In this case, it's okay, 1 up to M. Sometimes I will denote this by square bracket of M, such that each subsystem, so let's say, so I belongs to IK. So K here is from 1 up to R. U I squared, that's less or equal than, okay, let's say 1 minus epsilon squared, right? So what happens is that this is sometimes called a Bessel bound. Yes. Exactly, yes. So R, yes, so R has to be independent of M. So maybe I should put those quantifiers like in the very beginning, right? That there exists some constants delta, that if you have vectors which have small norms, let's say, vectors have small norms, they form Parseval frame, there exists an R, and there is also epsilon, where you can split your collection of vectors into piles, R piles, but each of them will have a Bessel bound which will be reduced from 1 to, but at least by some kind of small epsilon. Right, so that's what. So R has to be independent of the dimension, right? So it's and the number of vectors. And this was shown by Weaver to be equivalent to Cadison-Singer problem. And once you and now this is a theory. Yes, exactly, of M. So right, so we have finite number of vectors. So we put them into R piles, and each of them, when you compute those inner products, you get a lower bound than what you had before. This is a conjecture, but now it's also a theorem. Well, but this conjecture, when it was first formulated as conjecture, it was shown to be equivalent to Cadison-Singer problem. And yes. Right, but R has to be independent of both. So maybe I will say R is independent. That's important, of M and the D dimension, right? Exactly, because you can always maybe take R equal to M and like small. No, but no, you can. Yeah. Yeah, they should be in the very beginning. Yes, exactly. Yeah, but exactly, there is delta. Okay, I'm not saying for every delta. Yeah, yeah. Yeah, if it's yeah, of course, delta will have to be smaller than 1 too, because. Pardon me?
One that they use.
Yes, exactly. Then that's why you can see that. Yeah, usually delta has to be less than 1 to for this to be meaningful. Otherwise, yeah. For every U, yeah. I mean, because this is the that's the Parseval frame condition. The last one, okay, of course, it's also for all U. Of course. Yes, uniform estimate, exactly. Yes, exactly. Mm-hmm. Okay, maybe. Yes, exactly. But that's okay. So that's the conjecture. Okay, so maybe an example that it's worth to keep in mind. Let's do something that we know. Maybe there'll be not too many questions about that, but let's start from a system that we know is orthonormal basis, Fourier basis. Right?
Sorry.
Yes.
So this R is independent of M. What does it mean?
Right, because these are like the conjecture says exactly R is a number. So I should, yeah, the conjecture says there exists delta. Delta will have to be definitely, there exists epsilon, there exists R, so that, yes. But it's very easy conjecture, right? It only uses inner product stuff. I mean, you could state this to a student in a, well, who knows linear algebra. And okay. But but when you think about this, okay, let's start from orthonormal, like maybe it looks very simple, but like example that we should keep in mind, let's start from orthonormal basis of L2 of 0, 1. And then what I will do, I will construct a Parseval frame just by the usual way, by restricting to a set S. So S is set of, let's take S. So S is a Lebesgue measurable subset of positive measure. And then what will happen is that the same vector, the same Fourier system is a Parseval frame in L2 of S. So, and this is sort of, it's a Parseval identity. I'll still write this down. So when you compute the Fourier coefficients, and this is just the usual product, you get Parseval identity, and this happens for of F L2 of S, right? But then what happens is that because we treat our Fourier functions, I mean exponentials, as living on S, their norms, maybe with the norm squares, are equal to measure of S. So of course this is, so the system stops to be orthonormal, but becomes a Parseval frame. So for example, like this is this example that you have, and now maybe I'll just tell you a fact. I mean, if you wanted to prove this kind of Weaver's conjecture just by choosing a random choice of partition of integers, so random choice, so random partition of integers, when you take random partition of integers into those sets, basically you have R sets, and with equal probability you choose that you land in either of the sets. So this this will fails Weaver's KSR with probability 1. So I should probably say there, I forgot about one quantifier, maybe I'll put it here. There exists a set S, right? You can find a nasty set S, right? that the usual, like a random choice of partition will actually get you, yes, will not get you that bound with probability 1. So we are looking for event. So if we hope that something like this is true, we are looking at the event of probability 0, right? That's okay. And now okay, so let me tell you how this was solved. Some coefficients, exactly, because this is a Parseval identity. When you think of functions on L2 of S, no, it doesn't. It doesn't. Yes, exactly. But F has to be really like support of, you think of this as subspace of L2 of 0, 1, and functions that support of F is, so this is just support of F is in S, right? So this is just Parseval identity for functions. I forgot about square here, of course. Yes, that's okay. So how to so this is actually not, well, Weaver's conjecture is true, and how this is shown. Okay, let me just formulate this as a theorem. Maybe I'll put this. Okay, so theorem. And this is Marcus Spielmann-Srivastava, I think published in 2015. Okay, so I will formulate this in terms of random matrices. So let's say, suppose x1, x2, up to xm are positive definite d by d random matrices, actually of rank 1 initially, that take apparently many values, such that okay, what they satisfy. So when you take expected values of those random matrices, and I sum this from I equal 1 up to m, I get identity, or maybe I get something which is less or equal than identity, right? The other thing that you assume is that the expected value of the trace of each of these metrics is at most epsilon. So here there is also epsilon floating around, like epsilon positive, right? Right. Yes. So for what do you want to take for x1?
That's what I worried about. You have root one matrices like Z transpose, where Z is a Gaussian being zero.
Like a vector. Yes.
Those those is rank 1, but the expectation of those is the identity.
Of course, and that can happen. No, not at all. In fact, exactly, it doesn't cause the problem at all. In fact, here we assume that they need to take fun, because the same result maybe is true without this assumption, but the most interesting part of this result is actually when those random variables take finitely many values. When taking infinitely many values, I think this result will be okay. Let's continue. Then what is the conclusion? The conclusion is that the norm of that sum of those random matrices is bounded by that quantity 1 plus root of epsilon squared with positive probability. So probability of the event that this is, you have this happens with positive probability. Yes, so that's the Marcus Spielmann-Srivastava result, and this result actually implies. So MSS implies. Okay, so I'll try to explain it like this. It will imply something called selector version of KSR, and this will imply actually Weaver KSR conjecture. That's what I'm claiming. So even though, like, when you compare this, what is on that board with that, it doesn't like there's anything have anything in common. Maybe if you haven't seen this before, but actually this result implies. No, R could be arbitrary. Well, rank 1, yeah. Here, yes, it's harder to prove that for small values of R, but this result, this implication will be true for every R. Like this MSS result is so strong that implies any of those, including case 2. And let's see, what was my plan? Okay, I can probably only just I will say one thing. I mean, that this assumption here, that, well, my result, but it was also discovered by other people, is that, so this is the result of MSS, and then the result that one can observe is that this rank 1 assumption, so this is myself, there is Michael Cohen and Brandon. I mean, yeah, people observe that, yeah. But we have done this independently. This rank 1 assumption is really not necessary. You can just throw it away and the result is still true. Okay, but let me.
So, you mean not positive definite, you mean non-negative definite?
Yes, exactly. So, sorry, positive definite, I mean positive semi-definite. Yes, okay, so positive semi-definite. Yes, so they really, I mean, when I say positive definite, it means positive semi-definite, right? So, okay, so let's see. So let me follow my plan still. Yeah. Okay, so to show this, let me just, because in my title of talk, I had selector version. Let me still state selector version. Okay, so selector form of case R, which will be, okay, so let's see, selector form. And I will state this in the following way. Okay, so selector, and that's a theorem. Okay. So suppose UI, and here I'll be really general. So my collection of vectors can be actually also, suppose this is a Bessel sequence with bound 1 in some Hilbert space H. Maybe think of Hilbert space as CD, but it really doesn't matter. So okay, so what it means that I'll write this in the following way. So this is okay. I once over I u I squared. That's equal then 1 squared for all u in H. So that's one assumption. The second assumption is, as before, we assume that the norms squared are bounded by I use delta for all I. Right, so it's essentially the same assumptions as in the usual Weaver KSR, but then I have one extra assumption. Suppose also that that JK, I have some kind of partition. JK is a partition of the index set I, such that each set JK has at least R elements. Right, so we somehow put those vectors into piles that vectors are vectors. Okay, so then the conclusion is there exists a selector J. What is a selector? This means that J intersected with any of these sets JK, we choose one element, right? For every K, so for every of the subset JK, we take one element, such that the corresponding selector. So when you look at UI squared, okay, that will be less or equal than. And let me just make sure that I will not lie this. So this is Bessel with bound, yeah, bound, and the bound will be 1 plus root of R plus root of delta squared. And here is the number of this squared, and that's for all U in H. Okay, so that's the selector form of this result. So, okay, so maybe I'll try to explain what is the relationship between, okay. how, yeah, let's see, how MSS result implies selector KSR result and how this implies KSR result. It's really not good. Yes, exactly, one subset J. So you see, on the surface, it looks, yeah, exactly. We have only one subset J. So exactly, so it looks like this result is weaker, like selector result looks like it's weaker than this result because here we have extra assumption, right? But I claim that this is actually stronger, like this selector result implies this result. But before I do this, I would like to also show that how MSS implied KSR, and just so that you can see. Let's see. So maybe this is how do I do this? So this is still the KSR conjecture. Maybe I'll keep it for now intact. Let's see. And now where is the eraser behind me? Okay, in this. By the time, okay. I was here pointing. Exactly. Okay, so. Okay, so let's. But just give you a flavor how these things are done. Okay, so let's try to argue how MSSS implies selector KSR. That's actually not difficult at all. Essentially, you have already set up. So, right. Yes, exactly. So, this is the result that we have. So I'll define random vectors, VK. Yes, because, yeah, so we have this partition. So random vectors VK, that VK is K runs over K, that have values in, let's say, the Hilbert space is H, so they will have values in H. So R copies of H. So, right, because what we do, but how those random vectors are defined? Because we have those deterministic vectors. Okay, so the set VK, so the vector, so this vector V, let me just write like this, vector VK takes values UI, where I belongs to JK with probability 1 over R. So essentially, in this selector result, what we have, we put our vectors in piles. Well, let's say they are equal to R. If they are larger than R, then it's not really a problem. So, right? So this is maybe set J1, J2, and so on, JK, right? So for each of these piles, we have a random vector V1, V2, and maybe VK that we choose randomly. Those are vectors UI that are indexed, right? Okay, so that's what we do. So now, R, but if it's not equal to R, throw out those vectors. Yeah, exactly. So if there are more vectors in a pile, then just forget about those, throw them away. I mean, just, right, okay.
More strong because you make a more restricted choice of these sets J.
Yes.
There it says there's a partition exists, and there you say what it's looking like, because you always take these set J, which
yes,
uniform set J, which is independent of R.
Right. Yes. Exactly. So maybe that's, yeah. Okay, but let me just but we are talking about the implication, how this implication. Yes, exactly. But I was still trying to explain quickly this one, how MSS implies this. So okay, so now when you look at, we just need to take, okay, so what is our random matrices xk are just vk, or maybe this is like vk. These are rank one, because, right, this will be rank one random matrices. And when you compute what is the expected value of that, right, expected value of xk, essentially, and here I made a small mistake. There has to be normalizing factor. There has to be square root of r present here. So when you compute the expected value of that, what you will get, maybe let me see if this is right. What you will get, because, okay, so you get sum I belongs to jk, and then you are, so with equal probability 1 over r, we choose, and this vk takes values ui, right? So, but then there will be, yeah, but that's the issue. But there is also r coming from those. So I already make mistake here. There is no, there is just, so vk takes values. Yeah, so let me just, I always mix up. So each vector vk takes values square root of r times ui. So then when you take, okay, so here, yeah, so this will be vk, this rank 1. So then when you compute this, you get r. Okay, so what you get here is just summation I over jk ui. So now when you sum this over, so now when you put additional sum here, sum over k in k, expected values, what you get sum over I, sum k over k, sum I over those piles jk ui, but then you get the entire sum, right? And this entire sum, by our assumption, we assume that this is less than the identity, because that's what we assume. Okay, so that's by the assumption that we have here, right? And then we also need to check what are the traces, but the traces, I mean, I will just do this really quickly. The trace of that expected value of the trace of xk, that's just, the trace of this will be just the expected value of the norm of vk squared, but that will be less or equal than, there is this r times the norm of ui, but ui squared, we assumed it's less than delta, right? So that's the assumption. So that will be r times delta. So then what we'll know that there is an event where the norm of this is less than 1 plus, but what is our epsilon? Our epsilon is actually, that's our epsilon, right? There is event, but this event is just a choice because we are choosing those vectors randomly. So the event that we are looking at is just that selector, right? I mean, where we choose each vector, there is a choice of vector from each pile, so that what happens is that, okay, so what will happen is that there is a choice, so there is a J selector, so that when you take this sum of ui, and then you have ui, and you take operator norm of that's less equal than 1 plus square root of epsilon. The square root of epsilon is, and here already made a mistake with this normalization. There should be an r, because that's a, right, because there is square root of r here, and then, okay, and then it's 1 plus r delta squared. And then when you divide, okay, so, and then when you divide this, everything divide by r, you should get exactly, you get exactly this bound. So yeah, I'm sorry. Okay, but that's how. So it's really easy. I mean, it's a sort of easy application of MSS. And maybe coming back to your question, how does this imply? How does let's see, selector KSR implies KSR? It is just because you can use some kind of, okay, so let me just maybe erase, let's see, what do I can erase? Maybe I can, now I don't need this result. So let's see. So let me just, yeah, so let's forget about MSS result. Let's just see how the selector result SR implies KSR, okay. So let me try to explain that. Okay, so what do we want to do? We want, we want to somehow prove the Weaver's KSR conjecture, but knowing KSR. So let's do the following. So let's start from, let's start from vectors, let's say U1, UM, that are in our finite dimensional space. And now let's consider the space like D copies, R copies of the same space, right? So we start from these vectors, and we essentially what we'll do, we'll place those each vectors UI in each copy of that space. So what we have, let's say we have, like, I can probably say that we have vectors VI K. I will go from over M, and K will be over R, where what we do, we just okay, so let me just maybe write this down. So VI1 will be just UI, and then 0 everywhere in all components, and the last one UIR is just, okay, replace in the last UI. Right? So we essentially place this vector UI. Well, okay, so our goal is to find this partition, right? So we really don't know where this vector UI we can put, so we put it in our different possibilities. So now those vectors VI, they live. These are vectors in yes, exactly, in CDR. Okay, so now what we do next, we just need to make sure that I need to tell you what is that partition here. This partition here, JK, is essentially the dump partition where, so that's the set JK, or, well, my indices are off, so I should probably be using, okay, but let's say JI. Okay, so JI, so this is because my set, my index set here actually is M cross R. So essentially, so this JI is, yes, it consists of R vectors, but it's essentially the same vector, but placed in R different copies of the same space, right? So then what we do next is that, so now the selector KSR, what this implies, it implies that there is a selector, so there is a choice of placing those vectors that will give us this norm less than what is here. So there is a J selector, but selector of those, but this selector is equivalent to, it gives us the partition actually, partition I1 IR of the original index set M, because we started from M vectors, right? And then what will happen is that we'll get this kind of bound, but for the vectors, but what will happen is that we'll get this bound UI squared. So this will be less or equal than, well, the same quantity, but that will happen for each of the, like on each of subspace, you'll have that bound, and therefore you'll have this bound. You'll have this bound. Yes, right, because because this bound that what we have here, it's actually this bound happens, this inner product here, except this is happening in the space CD, but R copies of, so CDR, right? I mean, in a larger space. And then when you look at what's happening on each components, you'll get that. Implies, but no, it does. It's not. For this choice of selector, because this is a dumped selector, right? Because my vectors here, you see it's a very good question. My vector here is, you see, I have the same vector living in different copies of the same space. So yeah, this is for this type of partition, yeah, it's exactly. But then this selector KSR is much more general. I mean, they could come from totally different partitions, and then you cannot deduce the other direction. Yeah, but for this particular, yes, yeah. Okay, I hope at least maybe one person in the audience didn't get lost because he has questions mark. Yes, exactly. So, but no, I have still like 15 minutes left, and I think I will be, so there is also a higher rank version of this selector result, but okay, so my next plan was study higher rank KSR, but okay, maybe I'll do this basically by, okay, so because we have proven this MSS result also works for higher rank, maybe you can do the following. I'll do this in red. So, okay, so you can, instead of this Bessel sequence of bound one, what you can have TI. Okay, so TI, these are positive definite or semi-definite, let's say positive operators, trace class operators on H. So I'll just push, I tell you how far you can push this result. So you can start from positive trace class operators on H. This condition that we have here, this will be just saying that TI, sum of TI, I goes over I, that's less equal than identity. Right? And this sum is infinite sum, but you understand this as convergence is strong operator topology. This condition here on the norms will say that the traces of TI are less or equal than delta. And then this assumption doesn't change. You have partition and you want to find selector. So the conclusion here will be that there exists a J, so that when you take a sum TI and you look operator of that will be less or equal, and this bound is still the same. So that's, doesn't matter whether I put operator or not. Let me just put this less or equal than 1 plus root of R plus root of delta squared times identity, or just, right? So that's, if your operators TI, so think of this TI, if there are rank, when you have vectors UI, you can always construct rank 1 operators, and in the special case, when you take those rank 1 operators of the form, given by those vectors, then you get the previous result. Okay, so now let me tell you what are the applications of this. Okay, so let me start. So because I started to talk about exponential frames, and that's what I would like to end up. Okay, so maybe I'll use this blackboard. We still have time. Okay. So so what can you do with the selector results? Okay, so let me start from this. So that's a theorem. So suppose S is a subset of the unit interval, and S has positive measure, and you have epsilon. So what we can prove is that the following: there exists a synthetic set, lambda subset of integers. Synthetic means such that so the first part is, if you write lambda as let's say lambda 0, lambda 1, you put elements of the set in the increasing order, right? So what we know that the gap of that set lambda, it's finite gap. What is a gap? Gap is the infimum, it's a supremum of differences between consecutive elements of your subset, right? That's the gap. So the gap will be bounded by some constant divided by the measure of S times epsilon squared. But more importantly, what will happen is that the set of exponentials, So E lambda, so that's e the power 2 pi I lambda x, lambda runs over that. That will be, that's a resequence. Resequence in that space L2 of S, but with bounds. Okay, maybe I'll write just what it means. Okay, resequence, it's dual notion to the frame. So when you take, let's say, En, okay, but, okay, so you take linear combinations of complex exponentials, but only frequencies in lambda, because that's what we are claiming. So maybe the square. So this is controlled. Okay, so from above, this will be like, there will be 1 minus epsilon measure of S, and then you sum of A n squared. And then on the other side, you have pretty much the same bound, but with 1 plus epsilon measure of S, sum of A n squared. And this is true for all A n in little L2 of lambda, right? So you almost get like an orthogonal system, right? Because that's, well, modulo that constant, but it has to be a constant because the vectors En have normed the measure of S. So you almost get something that's like an image of orthogonal system under invertible operator that has the ratio of this constant 1 plus, I mean, it's arbitrarily close. But then the closer you want this to be orthogonal system, the more, the bigger gaps are, right? So that's one result that you can prove using the selector result, but I will not maybe explain how this is done. So this is there is some history of this result. The first version of this result was shown by Burg and Safriri, where they shown the existence of sets of positive density where that are resequences. And here you have, using the selector result, you can show the existence of resequences that will be actually synthetic, so that the frequencies that you choose are not far apart. I mean, they have those gaps. Okay, so, and then the second result that I would like to explain, I think Professor Olewski is in the audience, or yes, he's okay. He's maybe it's extension of a result of Professor Olewski about existence. So this was existence of exponential frames on unbounded sets. So that was a really nice application again of Cadison-Singer, and we can sort of improve this result a little bit. Okay, so this time what we are saying is the following. So suppose S, we start from the set S of finite measure. So this is any measurable set. And we assume that, okay, it has finite measure. Yeah, we have also epsilon positive. That's somehow the tightness parameter. So then we claim there exists a subset lambda of R such that the following things happen. So the first thing is that, yeah, we would like the set of exponentials E lambda to be a frame in that space L2 of S, but the frame bounds will be almost tight. So we frame bounds that are actually 1 plus or minus epsilon. There is a constant A, which, I mean, that's S over epsilon squared. I think that's what it is. So essentially what it means is that, what are the frame bounds? This means that when you take the sum, okay, when you compute the Parsova identity, that will be, and maybe you do this for F in L2 of S that have norm 1, right? That you have bound from below. Yeah, it's almost tight. And this is like a frame redundancy. I mean, well, so it's almost tight, okay. But then the other thing that we have that that the frequencies that we choose are actually uniformly discrete. So we can separate this. So when you take infimum of lambda not equal to mu that belongs to lambda minus mu, that's greater or equal than some other constant, and it's epsilon squared over the measure of S. So there is some control on those frequencies that you choose. I mean, so not only you can have, so I hope that I was able to improve this result of Professor Olewski, Ulanowski, and Nitzan in two directions. One, you can get almost tight frames. And the second one is that the frequencies that you choose they will never cluster. They'll be like separated. And the separation depends on basically on epsilon. If epsilon, the closer frame bounds you want to be, I mean, the tighter you want to have a frame. So epsilon very small means that your separation gets worse. I mean, this will, but at least you have bounds from below on the separation. Okay, so, and maybe this is, since it's a talk about discretization, I can tell you one more result that I can prove using those techniques. Maybe you can still watch this, and hopefully I didn't make too many mistakes when I copied this from my notes, but okay, so the last result is, because, yeah, it's quite, yeah, it will involve, yeah, so let's call it like theorem about discretization of continuous frames. Okay, let me just explain what this is. Yeah, I think I have just enough time to do that. So suppose X mu is a measure space. And yes, we have here, we have a family indexed by this measure space, but these are trace class operators. Trace class operators. They depend somehow measurably on T, but and this trace class operator family, Bessel family. Bessel family, what it means is that, okay, but the way they are also, they are trace class, but they are also, the traces are these are positive operators, right? You assume that, okay, so maybe I should say T maps T is measurable. The fact it's Bessel means that when you integrate those operators over X, this is less reliable than identity. So this is Bessel family with bound 1, I should add. Right, so this integral is interpreted in strong operator topology. It's not operator, yeah, okay, so what you can interpret this. And the other thing that you assume also that the traces of those PT, they are less than delta, so they're uniformly bounded. So whenever that happens, then you can find a sampling, let's say sampling Tn of your measure space X, and a constant, okay, exactly. Okay, such that the following will happen. Okay, so when you sample this, so now this is a discrete sum, and you compare this with the frame operator, which is just this integral, right? So, and there will be constant 1 over A. So you can make it arbitrarily close. You can make it less than epsilon, but there is this constant A. So for some, we'll just move like this. So for some A, that's proportional to, I guess, delta over epsilon squared. So this is like a redundancy constant, right? So what we do here, okay, so what I'm trying, maybe this is a bit more general than for most of you to see, but if you know what is continuous frame pi t, continuous frame, you can always construct this family. I mean, this is just rank 1 operators Phi tensor Phi t, right? So then you have this continuous frame that's, let's say, bound 1. You assume that their traces are small. Traces small means that just the norms are squared or less than delta. Then you can always somehow find a sampling which approximate, this is a frame operator essentially of, right? You can, and there is this redundancy, well, the constant that has to somehow depends on delta, the bound that you have here, and epsilon is how close you want to approximate your operator. So essentially this result, that what maybe the result on exponential frames is like a special case of that. I mean, yeah, because except this is for very concrete frames of exponentials, whereas, yeah, this result holds in greater generality. Okay, I think I will stop here because.
Thank you, Marcin. Question, comment? Mario?
Actually, but let me ask one. So the discretization of the frames, can you know the work of Green Eagle, right?
Yes, exactly.
Better than
yes, so this is better in two ways. I mean, I would say then, first of all, the result was only for rank 1. I mean, it's just, okay, so that's one. But the other result is, the other thing is that they were not able, in fact, I spent so much time trying to understand the proof and improve. The result, once they start from continuous, let's say from Parseval frame, because Parseval frame, they show existence of discretization, but it will not be tight. I mean, they can only get frames with the ratio of upper to lower frame bound that's 2 plus epsilon. So it's very strange. I mean, 2 plus epsilon. And in my case, I can get arbitrarily close to 1 plus epsilon. So that was my biggest motivation to study that, because why is it 2 plus epsilon? Why starting from Parseval frame, something which is the ratio of the upper and lower bound is 1, why can't you get arbitrarily close to 1? Okay, so now, yeah, so it can be done. So that's the improvement. And then of course you have this higher rank. Yes, but that's an extension of Freeman-Spiegel result, yes, of course.
Other question?
What is condition of the matrix?
Yes, what are the conditions on matrices? So what is the higher rank? So here in the red chalk, let's see if I still have red chalk. This is the selector higher rank, right? Higher rank selector. So in fact, these are matrices, or even could be positive, because you can somehow extend this to positive trace class. So the most general is positive trace class operators. So for example, finite rank, but there are positive, positive operators. You assume that they add up to at most just operators. No, not rank 1, exactly. It could be arbitrary. Yes, but the traces, you have control on traces, and there is no, it's not. This result, I think it's due to myself, at least in the selector form, but I think it was also observed by some Chinese people. There's some paper, I think maybe, so I'm not claiming that it's only, the selector version is for sure mine, but it was, once you have MSS result for higher rank, you can have this result, maybe for matrices, but then you can also have for operators if you, pardon me? This is my result, yes. Okay. Yes, exactly. Yeah, that's my result. At least let's claim it like that. I mean, that is, yeah. Yes, exactly.
If not, let's thank you.